Imagine drifting through space. No planets nearby, no stars close enough to warm you, only darkness and distant points of light. Then, something begins to change. At first, you notice nothing unusual. Your spacecraft instruments detect a massive object ahead, but visually, it appears almost empty, a dark circle surrounded by distorted starlight. You are approaching a black hole. Few objects in the universe inspire more curiosity or more misunderstanding. Black holes are often portrayed as cosmic vacuum cleaners that swallow everything instantly. But the reality is far more complex. If you were to fall into one, the experience would not involve being suddenly crushed or instantly destroyed. Instead, the journey would unfold in stages, governed by the laws of gravity, relativity, and space-time itself. To understand what would truly happen, we must begin with the physics that created black holes in the first place. What a black hole really is. A black hole is not a hole in the usual sense. It is a region of space-time where gravity becomes so strong that nothing can escape once it crosses a certain boundary. This boundary is called the event horizon. The concept of the event horizon emerges naturally from the theory of general relativity. Developed by Albert Einstein in 1915, this theory describes gravity not as a force, but as the curvature of spacetime produced by mass and energy. When enough mass collapses into a sufficiently small region, spacetime curves so strongly that all possible paths point inward. Once an object crosses the event horizon, every possible future path leads deeper into the black hole. Escape is no longer physically possible. But from the outside, something strange appears to happen. Objects approaching the event horizon seem to slow down. Their clocks appear to tick more slowly. Their light becomes increasingly redshifted. This phenomenon is known as gravitational time dilation. To distant observers, an object falling toward the event horizon never quite appears to cross it. But for the person falling in, the experience is very different. Approaching the event horizon. Let us imagine you are approaching a large black hole, specifically a supermassive black hole like those found at the centers of galaxies. One famous example is Sagittarius A star. Supermassive black holes contain millions or billions of times the mass of the Sun. Because of their enormous size, the gravitational gradient near their event horizons is relatively gentle compared with smaller black holes. This means you might cross the event horizon without immediately noticing anything unusual. Your spacecraft instruments would detect extreme gravitational effects, but visually, the most striking phenomenon would be gravitational lensing. Light from distant stars would bend around the black hole. The entire sky would appear distorted, stretched, and warped. Stars behind the black hole would form rings of light around it. These rings are known as Einstein rings, predicted by general relativity. The closer you move toward the event horizon, the more extreme the distortions become, but physically, you might still feel almost weightless. Gravity in freefall does not feel like a force. Inside your spacecraft, everything would float normally. However, the real danger lies ahead: spaghettification. As you move deeper into the gravitational field, tidal forces begin to increase. Tidal forces arise because gravity pulls more strongly on parts of your body closer to the black hole than on parts farther away. This difference in gravitational pull stretches objects along the direction toward the black hole while compressing them in the perpendicular direction. Physicists sometimes refer to this process informally as spaghettification. If the tidal forces become strong enough, they can stretch any object, including a human body, to an extremely thin stream of matter. Whether this happens before or after crossing the event horizon depends on the size of the black hole. For small stellar mass black holes, tidal forces near the horizon are extremely intense. In such cases, spaghettification would likely occur before you ever cross the event horizon. For supermassive black holes, the event horizon can be large enough that tidal forces remain manageable at that boundary. In theory, you could cross the horizon without immediately being destroyed, but the deeper you travel, the stronger the tidal forces become. Eventually, they would reach destructive levels. Crossing the event horizon. One of the most surprising predictions of general relativity is that crossing the event horizon would not feel like passing through a physical surface. There is no wall, no sudden shock, no visible boundary. From your perspective, you simply continue falling. However, something profound has changed. You are now inside a region of spacetime where all possible paths lead inward. In a sense, the direction toward the center of the black hole becomes as inevitable as the direction toward the future. Just as you cannot stop time from moving forward, you cannot stop yourself from moving toward the center. No known physical force can reverse that motion once the event horizon has been crossed. Even light cannot escape. What happens at the center? According to classical general relativity, matter falling into a black hole eventually reaches a region known as a singularity. A singularity is a point where density becomes infinite and the curvature of spacetime becomes infinitely large. However, most physicists believe that this description is incomplete. General relativity does not include the principles of quantum mechanics. At extremely small scales and extremely high densities, quantum effects should become important. A full theory of quantum gravity would likely modify the classical picture of the singularity. Unfortunately, such a theory remains one of the greatest unsolved problems in modern physics. Because of this, we cannot currently describe with certainty what happens at the very center of a black hole. From the outside perspective, while you fall inward, observers far away would see something very different. Because of gravitational time dilation, your motion would appear to slow dramatically as you approach the event horizon. Your signals would become increasingly redshifted. Eventually, they would fade entirely. To distant observers, you would appear frozen near the horizon. In reality, you would have already crossed it. This difference between perspectives is one of the most fascinating consequences of relativity. Conclusion: the edge of known physics. Black holes represent the limits of our current understanding of physics. They combine extreme gravity, relativistic spacetime, and quantum uncertainty. Studying black holes may ultimately lead to new discoveries about the fundamental nature of the universe. If you were to fall into one, the journey would not be an instant destruction. It would be a gradual encounter with some of the most extreme phenomena known in nature. From warped starlight to tidal stretching to the irreversible crossing of the event horizon, black holes reveal just how strange and powerful gravity can become. And they remind us that even today, the universe still contains mysteries that science has not yet fully solved.